Hey guys, so where we left off last time, we were talking about the fact that there's these two different types of probability. One is called the experimental, or as the book likes to call it, estimated probability. And that's when you actually do a chance experiment over and over again. You run a bunch of trials and you make observations of the outcomes every time you run a trial. And then you use that data from your outcomes and your trials to get a probability number that comes from your experiments or is in reality estimated because it's often not the same as the theoretical probability. So we're going to do lesson 2 today, and this focuses all on experimental or estimated probability. And then I'm going to ask you to do a Desmos activity that is about estimated or experimental probabilities. And then tomorrow we'll do lesson 4, which is more about theoretical probabilities. And I'll ask you to practice that a little bit. And then on Thursday, you'll do a Desmos that kind of looks at a little bit of the difference between experimental and theoretical probabilities. I think most people find experimental or estimated a little bit easier. Theoretical is a little bit more challenging, and we'll probably spend a little bit more time on theoretical. All right, so this is the important formula here, or equation, whatever you want to call it, for experimental probability. And what this says is, imagine you are running a chance experiment a bunch of times that had to do with adding numbers, and you wanted to know what is the probability of the numbers you're adding up to greater than or equal to 5. So here, where it has a capital P, when we're working in probability, that capital P will always stand for the word probability. And then what the thing that you're trying to calculate the probability of, like the outcome that you're looking for, sometimes referred to as the desired or favorable outcome, you'll write that in the parentheses next to the capital P. So what this says is the probability of the sum being greater than or equal to 5. So this doesn't mean like P times sum greater than 5, or like it's not telling you to like distribute the P over these words and stuff like that. It's just a different way of using parentheses in math. And so in this case, the probability of the sum being greater than or equal to 5, or whatever event or outcome you're trying to test for, you would put in here. And that's always going to equal the number of observed occurrences of the event. That's just a fancy way of saying the number of times the thing that you're trying to see happened. Another way people say this is number of desired or favorable outcomes. So in this case, if we were playing some game that involved adding up numbers and we were trying to calculate the probability of the numbers adding up to greater than or equal to 5, then on the top would be the number of times that the numbers added up to 5 or greater, right? The number of times that the thing happened. And at the bottom of the fraction or the ratio here goes the total number of observations. That's essentially just how many times did you try the thing. I prefer, instead of saying total number of observations, number of trials. How many times did you run your chance experiment? Okay, so number of times you got the thing that you wanted divided by the number of times you tried. Right? That's the whole like formula to it. It's really not that challenging, I don't think. Basically, you just you run a chance experiment a bunch of times, and then you divide how many times you got the thing you wanted by how many times you tried. And so if we were in class, we would actually be running these chance experiments ourselves. I'd have you guys like spinning spinners, rolling dice, stuff like that. But I don't know. I guess we can't really do it the way things are now. So instead, I'm just going to kind of go through some data. So the first game they're talking about is essentially what that formula was referring to on the other page, where it was talking about the sum adding up to greater than or equal to 5. They're referring to this game, actually, that's back on the first page of lesson 2. Imagine you have this spinner, and maybe I actually had an actual spinner thing here that I could flick, and you spin it once, and whatever number comes up the first time, you put in this first column. And then you spin it again, and whatever number comes up that time, you put it in the second column. And then you take those two numbers and you add them up. So I did this before I started the video. On my first spin, I got a 3, and on the second spin, I got a 2, and I added them up, and I got a 5. And then they wanted me to run 15 trials of it, right? So each 2 spins and adding the number counts as 1 trial. So here it says turn, but the real word we want is trial. So trial 1, I got a 3, a 2, and that added up to 5. Trial 2, I got a 1, a 2, and that added up to 3. And so these things out here would be referred to as the outcomes, right? Because they're the numbers I got when the whole trial was over. All right, and so they just want us to answer some basic questions about what happened in this data over here. It says, out of the 15 turns, I really want to get used to using the word trials, so I'm gonna change that to trials. How many times was the sum greater than or equal to 5? Okay, because I guess that's sort of the point of this game, is to see if you can get 5 or greater on your sum. So let's count the number of observations where that happened, or the number of outcomes where that happened, or how many times we got our desired outcome, which is the sum being greater than or equal to 5. There's lots of different ways to say what we're trying to do here. So I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I counted 10 trials where the outcome was a sum of 5 or greater. So I'll put a 10 over here as the answer to this question. All right, so what sum occurred the most often? Okay, so let's go back to the data. Just glancing at it, it looks like 5 happened the most. I got 1, 2, 3, 4, 5, 6. I got 6 5s. I'm just glancing at it. I don't think there's any other outcome that occurred 6 times. So I'm going to say that the sum that occurred most often was 5. What sum occurred the least often? Okay. Well, I see 1, 2. Are there any other 2s? No. And I see 1, 8. 1, 7. Okay, 2 6s, 2 4s. It looks like it's gonna be 2, 7, and 8 are the ones that happen the least often. In working with probability and statistics, we often have to list multiple things. It's okay to just separate them by a comma. So a comma. So I have 3 answers here: 2, 7, and 8, and I just put 2, 7, 8, if students played a lot of games, what proportion of the games would they win? So you win this game by getting a sum that is greater than or equal to 5. That's the whole point of this game, spinning twice and trying to get 5 or higher. Okay, so if I want to use experimental probability to answer this, it's going to be the number. Oh wait, let me write it properly. So the probability of, capital P, and then I'm going to put something that abbreviates what I'm looking for here, and I'm going to write it sort of below the P. See how it's a little bit lower? This is called subscript when you write like this. So the probability of the sum being greater than or equal to 5, well, that's going to be equal to the number of outcomes where the sum was greater than or equal to 5, divided by 15, because we ran 15 trials of the experiment. So I could have wrote number of trials there, but I know that the number of trials is 15, so I just put a 15. All right, so we count up how many times did I get 5 or better. I already did that, right? I did that for question 1. It was 10 times. So this is going to be 10 out of 15, and we can divide the top and bottom of this by 5, and so it's 2/3. So by my experimental data, I estimate, or experimentally, I say that the probability of getting a 5 or greater is 2/3, or 0.6 repeating, or 66.6%. All 3 of these are proper ways to write probabilities, but as a decimal is my favorite way. That's the way I'll do the most often, but you're allowed to do any of those 3. All right, so name a sum that would be impossible to get while playing the game. Well, you can't get a sum of 1 because you have to spin twice, right? and the lowest number you can get each time is 1. So you spin once, you get a 1. You spin another time, you get a 1. The lowest the lowest sum you could possibly get is a 2. So I would say that a sum of 1 is impossible. And also, just to be, I don't know, silly, I guess a sum of 4,032 would also be impossible. Okay, and what event is certain to occur while playing the game? I would say that the probability of getting a sum that is less than 10 equals 1. Okay, so let's read what this says. This capital P means probability, and then in the parentheses I state what I'm saying the probability of. I say the probability of getting a sum that is less than 10 equals 1. And remember, 1 is the same as 100%. So saying something has a probability of 1 is the same as saying it's going to for sure happen. What I'm saying is no matter what numbers you spin, for sure your sum has to be less than 10, right? You can't get a sum of 10 or 11 in this game. The highest sum you can get is 8. So for sure the probability of getting a sum less than 10 is 1 or 100%. So number 7 here says, based on your experiment of playing the game, what is your estimate for the probability of getting a sum of 5 or more? So we actually already did that. I just don't think the book expected me to be able to do that already because it hadn't showed me the formula. But the answer to that is this here again. Based on our data, because we got 10 out of 15 tries where the sum was 5 or greater, that comes out to 66.6% or a 0.6 repeating probability. All right. And so number 8 here says, based on your experiment of playing the game, what is your estimate for the probability of getting a sum of exactly 5? Okay, so this is the probability of the sum equaling 5. So I write sum equals 5 in the parentheses, and that's going to equal the number of times we got 5 divided by 15, because we ran 15 trials. All right, so let me just go back and count how many times I got a 5. 1, 2, 3, 4, 5, 6. Okay, so the probability of getting a sum of exactly 5 is going to be 6 out of 15, or 6/15. I see that the top and bottom are divisible by 3, so let me do that. Divide by 3 on top and bottom, and I get 2/5, which is equal to 0.4, which is equal to 40%. All those 3 ways are okay ways of representing your answer here. All right, so let's do a different chance experiment now about animal crackers. Let me switch to a new color. It says, a student brought a very large jar of animal crackers to share with students in class. Rather than count and sort all the different types of crackers, the students randomly chose 20 crackers and found the following counts for the different types of crackers. The students can now use that data to find an estimate for the probability of choosing a zebra from the jar by dividing the observed number of zebras by the total number of crackers selected. The same thing we were doing in the previous exercise. So the estimated probability of picking a zebra is 3 out of 20, or 3/20, or 0.15, or 15%. Those are all the same thing. And they got that by the fact that it looks like they pulled 3 zebras, or in other words, they had 3 observed occurrences of zebra out of the 20 trials. So 3/20. All right, so this means an estimate of the proportion of the time a zebra will be selected, a number of times a zebra will be selected, is 0.15, or 15% of the time. This could be written as the probability of zebra equals 0.15. All right, so let's move on. It says, if a student were to randomly select a cracker from the large jar, what is your estimate for the probability of selecting a lion? Okay, so this is just going to be number of times they chose a lion divided by the number of trials, which is 20. So they pulled 2 lions out of 20. So the probability of a lion equals 2 out of 20, which is the same as 1/10, which is the same as 0.1, which is the same as 10%. All of these are good ways to list your answer on that one. I'm going to stop always writing it in 3 ways, and I'm probably just going to start doing the decimal most frequently. What is the estimate for the probability of selecting a monkey? Okay, so that's just going to be the number of times they pulled a monkey, which was 4. So probability of getting a monkey equals the 4 times they got monkey divided by the total number of trials, which was 20. So let's see here, this is equal to 1/5, which is the same as 0.2. All right, what is the estimate for the probability of selecting a penguin or a camel? Oh, I'm sorry, I just realized I'm a little bit off screen. What is the estimate for the probability of selecting a penguin or a camel? Okay, so when you see the word "or," that tells you that both of these outcomes are favorable or desired. So I look for all the times that they pulled penguin and all the times they pulled camel, and I add those up because this is now one event, right? The way the book explains this is that getting a penguin is an outcome, getting a camel is an outcome, but when you have the choice between 2 outcomes, you essentially add those together, and that's called an event. So the event is penguin or camel, like the 2 outcomes put together make an event. All right, so let's look at how many times they get a penguin. That's 3. Okay, so it's gonna be 3 plus the total number of times they got a camel, which was 1. So 3 plus 1 over 20. Right, so when you use the word "or" in statistics, in probability, it makes your probabilities go up, right? Because if I give you the option to satisfy a favorable or desired outcome by doing this, or this, or this, or this, it makes it much easier, right? Like if I say roll a die and you win if you roll a 1 or a 2 or a 3 or a 4 or a 5, your probabilities just went way up, right? Because you have 5 out of 6 ways of winning. That's a lot easier than if I said you only win if you roll a 1. And it's also much better than if I use the word "and" instead. When you use the word "and" in probabilities, that makes things way harder. Because if I said you have to roll a dice and get a 1 and then roll a die and get a 2, that's way harder. Now you have to get a 1 and then a 2. So "or" sort of makes probabilities easier and makes probabilities go up. And the word "and" makes things more difficult and makes probabilities go down. All right, so this is the probability of a penguin or a camel. This is also 4 over 20, just like the last one. So I know that that's 0.2, and I should write what it is. It's the probability of, I'm gonna write P or C to abbreviate penguin or camel. All right, what is the estimate for the probability of selecting a rabbit? Okay, so the probability of getting a rabbit equals, how many times did they get a rabbit? Oh, there's not even a rabbit on here, so this is like a trick one, right? There's no rabbit. So, well, as far as we know, they only pulled 20 crackers from the thing. But as far as we know, based on our data, there's no rabbits. There could be a bunch of rabbits in the thing, but we have to, in the actual jar, but we have to go off the data we got from the 20 trials, and they got 0 out of 20 rabbits. So that's 0 probability of pulling a rabbit based on the data. That might not actually be true. There might actually have been a bunch of rabbits in the thing. All right, is there the same number of each animal cracker in the large jar? Explain your answer. So when we look at this data, they got more elephants than anything else, and kind of a lot of monkeys, and not very many camels and lions, or tortoises. And so you could conclude that there's probably more elephants or monkeys in the jar, and that would be a reasonable conclusion. Someone else could also argue, yeah, but you know what, they only pulled 20 out of a big old jar. Like, this might not be enough data to really say for sure. And so I think you could kind of go either way with this. I will say that if I was a betting person, that there are probably more elephants than anything else. But we don't know for sure. Okay, if the student were to randomly select another 20 animal crackers, would the same results occur? Why or why not? Probably not. The chance that a student would pull another 20 crackers and get this exact same set of data with like the 5 elephants, 3 zebras, if we're talking about one of those big old jars of animal crackers like from Costco or something, it'd be really, really tough to get those that exact same data again, right? It could happen. Probably not. I would say very small chance. All right, and then the last question, I think this is the end of the lesson. Yeah, so we're basically done. This question's important though, so I hope you're still kind of paying attention. It says, if there are 500 animal crackers in the jar, how many elephants are in the jar? Explain your answer. So we're going to use this probability, or you could kind of also call it statistical data, whatever kind of data you want to call it. We're going to use this data and the calculation we did, or I guess we didn't do one for elephant, to estimate or predict how many elephants are in the jar if there's 500. Well, let's go back to the data. We got 5 out of 20 elephants. So the probability of an elephant equals 5 elephants out of 20 trials, which is equal to a fourth, or 0.25. Well, then the way we should see that is that based on our data, we think that 0.25 or 25% of the crackers are elephants. So then we need to calculate what is 25% of 500, and that's our estimate for how many elephants we think are in the jar. So 25% of 500 equals 0.25 times 500, which is just a fourth of 500, and I can do that one in my head. That's 125. So based on our data, we estimate that there's 125 elephants in the jar. That's probably not correct, right? It's an estimate, but this is just how we use the data in these cases. All right, sorry this video was a few minutes longer than I usually like to make them, but oh well, that's the way it goes.